This is the last lecture in the series of lectures on global environment. And by the global environment, we mean the Earth's atmosphere and its effect on various parts of the Earth's total environment. We've already talked about the four elements of weather and climate: temperature, wind, pressure, and moisture. And it's very important that you understand each one of these elements of weather and climate individually. But it's much more important to understand how each of these elements of weather and climate are interrelated one with the other. For example, warm air has a tendency to rise, and as a result, warm air exerts a less amount of pressure on the Earth itself. Pressure itself contributes to wind. We've talked about high pressure areas versus low pressure areas. And air has a tendency to move in a horizontal fashion directly from high pressure to low pressure. We've also talked about the air having a certain amount of moisture in it. Moisture in the atmosphere in the form of a gas we call water vapor. And depending on the temperature of the air, water vapor will be released by the atmosphere. And as water vapor is released by the atmosphere, it changes its composition from a gas to a liquid. We call this process condensation. And so today, what we'd like to do is to look at all of these elements of weather and climate as they are interrelated with one to another. And we're going to see the resulting situation in terms of a specific weather condition that we often experience, and that is rainfall. And so, if you have any questions, raise those questions as I present these transparencies. The way in which we're going to talk about the effect of specific elements of weather and climate on the general total environment is by considering what we call the adiabatic process of heating and cooling. And this process includes all of the elements of weather and climate that we've talked about: temperature, wind, pressure, and moisture. So what you see here on the transparency is a diagram of the mountain with air moving from left to right as indicated by the arrows. And what happens is that the air is forced to rise over the mountain. And as it rises over the mountain, it cools off. And then eventually it gets to the other side where it descends back down the other side of the mountain, which is the leeward side of the mountain. And as air sinks or descends, it heats up. So this is a basic relationship that you need to remember as far as what happens when air rises and what happens when air sinks. As air rises, it cools off. As air sinks, it heats up. Now this diagram indicates a similar process by which air rises and cools off. But the way in which air rises in this instance is different, because what you have is air being heated in a certain location to a certain temperature. In this case, the air is heated to a temperature of 60 degrees. Now, in some areas, air is more likely to be heated than other areas. For example, during the summertime, on land areas, land has a tendency to heat up very quickly as opposed to water areas. Water itself heats up much slower than land. So during the summertime, as the sun's rays beat down on the Earth's surface, the land surface has a tendency to heat up very rapidly, and this makes the atmosphere just above the land heat up very intensely. And so what happens is that this heated air rises. The surrounding air, by definition, is much cooler than the heated air. And in fact, this is how a heated air or parcel of air is defined. It's defined based on the fact that it is warmer than surrounding air. And so as the heated air continues to get warmer than surrounding air, it begins to rise. And so again, where the heated air is at 60 degrees Fahrenheit, the surrounding air might be at only 50 degrees Fahrenheit. So in this case, the heated air is 10 degrees warmer than the surrounding air. And so we realize that air can rise as a result of it being forced to rise over an obstacle such as a mountain, or it can rise on its own as a result of simply being warmer than the air that surrounds it. Now we need to consider three things as far as our understanding of a specific weather situation as a result of rising air, whether it's forced to rise or whether it rises on its own. The first thing that we have to consider is the temperature of the rising air at certain elevations. If the temperature of the rising air is a certain degree at the surface, and so this is what this tells us as far as understanding the temperature at certain elevations. Temperature of the rising air on the one hand, and temperature of the surrounding air on the other hand. So what this shows over to the left is elevation or altitude in thousands of feet. So here, this indicates 0 feet for the surface, and 2,000 feet, 5,000 feet. These figures here indicate the temperature of the surrounding air. These figures over here represent the temperature of the heated parcel of air at 2,000 feet and at 5,000 feet. So again, in order to understand the specific weather situation that we want to come to understand, is that we need to differentiate between the heated parcel of air, which has a tendency to rise, and the surrounding air, which is essentially stable. In other words, it does not rise. And so according to this, we find that the surrounding air is at 43 degrees at 2,000 feet, and it is at 32.5 degrees at 5,000 feet. On the other hand, the surrounding air, or I should say the parcel of air, is 49 degrees at 2,000 feet and 32.5 degrees at 5,000 feet. What we need to understand now is how we get these figures. How do we come to a determination of the temperature of rising air and of surrounding air at various elevations? these figures tell us how we get the temperature of the surrounding air and of the rising air at 2,000 feet and at 5,000 feet. First of all, if you consider the surrounding air, you need to keep in mind, again, that we're not dealing with rising air, we're dealing with stable air. And so what we want to find out is simply the temperature of the air at certain elevations. And the way in which we get this is to use the normal lapse rate. Now we've already talked about the normal lapse rate, if you remember. The normal lapse rate is the rate that air cools off with increasing elevation per 1,000 feet. This is the normal lapse rate. The normal lapse rate specifically is 3.5 degrees Fahrenheit per 1,000 feet. So for every 1,000 feet that the air rises, it will cool off at an average rate of 3.5 degrees Fahrenheit. So this is the normal lapse rate. So we want to find the temperature of the air at 2,000 feet. We would multiply then 2, standing for the number of feet, times 3.5, which is the normal lapse rate, and you get 7. And 7 indicates that the temperature of the air will be 7 degrees cooler at 2,000 feet than at the surface. In other words, the air will be 7 degrees cooler than 50 degrees, which is the temperature of the surrounding air at the surface. And so we subtract 7 from 50, it gives us 43. So the temperature of the surrounding air at 2,000 feet is 43 degrees. We want to find out the temperature at 5,000 feet. We multiply 5 times 3.5. It gives us 17.5, which means that the temperature at 5,000 feet is 17.5 degrees cooler than the temperature at the surface, which is 50 degrees. So we subtract 17.5 from 50, and it gives us 32.5, which is the temperature of the surrounding air at 5,000 feet. So again, air temperature will decrease at a rate of 3.5 degrees Fahrenheit for every 1,000 feet in elevation. Okay, now the rising air, how does that decrease with increasing elevation? Well, the difference is that the temperature of rising air decreases at a much greater rate than normal decreases in air temperature with increasing elevation. And the rate at which rising air cools off is the dry adiabatic rate. The dry adiabatic rate is the rate at which dry air cools off as it rises. So, for example, if air is heated to a certain temperature, as we saw earlier, to a temperature, say, of 6 degrees Fahrenheit, that air will begin to rise because it's more buoyant, it's lighter than the surrounding air, and the minute that parcel of air rises, it's going to begin to cool off. But the rate at which it's going to begin to cool off is 5.5 degrees Fahrenheit for every 1,000 feet that it rises. Okay, and so understanding this, we want to know the temperature of the rising air at 2,000 feet, similar to the way we got the temperature of the surrounding air at various elevations. We multiply 2 times 5.5, it gives us 11. And this 11 indicates that the rising air will be 11 degrees cooler at 2,000 feet than it is at the surface. In other words, it's going to be 11 degrees cooler than 60 degrees. And so we subtract 11 from 60, it gives us 49 degrees. So the temperature of the rising air at 2,000 feet is 49 degrees. If we want to know the temperature of the rising air at 5,000 feet, we do the same thing. We multiply 5, standing for 5,000 feet, times 5.5. It gives us 27.5. And we subtract 27.5 from 60, and it gives us 32.5. So the temperature of the rising air at 5,000 feet is 32.5 degrees Fahrenheit, which is the same temperature as the surrounding air at 5,000 feet. So the rising air will cool off, and it will continue to rise until it reaches an elevation by which it gets to be the same temperature as the surrounding air. And at that particular elevation, essentially the rising air will merge into the surrounding air because it will have the same temperature. Keeping in mind that the way in which we define this parcel of air is by the fact that it has a higher temperature than the surrounding air. But whenever it reaches a point where the temperature of the parcel of air is the same as surrounding air, we don't want to have a parcel of air because it has merged into the surrounding air. And so at this particular point, you will have atmospheric stability because you will not have any further rise of air. This is one situation, a situation by which we do not consider the amount of moisture that's in the atmosphere. We simply consider the temperature of the rising air and the temperature of surrounding air at various elevations, and the way you do it. Now, secondly, let's consider the fact that the atmosphere, say that is heated to a certain temperature, has a certain amount of water vapor in it. Let's assume that the air that is heated to 60 degrees Fahrenheit has 1.9 grains of water vapor in it. And that the dew point that is needed for this air to condense is 30 degrees Fahrenheit. In other words, air which has this much water vapor in it, the air has to cool off to a temperature of 30 degrees Fahrenheit in order for this water vapor to be condensed out. Okay, and so let's look at what happens. Again, you have the situation by which air movement is created as a result of differential pressure, for example. Air moving from high pressure to low pressure, it meets an obstacle such as a mountain, and it flows over the mountain. It cools off. It cools off at the dry adiabatic rate, 5.5 degrees Fahrenheit per 1,000 feet. At 2,000 feet, the air is 49 degrees. At 5,000 feet, the air is 32.5 degrees. But the difference in this example from the previous example is that we're assuming that the air has a certain amount of water vapor in it, and that this water vapor will condense out at a certain temperature. Okay, and so we go about finding out the temperature at a certain elevation the same way. In other words, we want to find out the temperature at 5,000 feet. We simply multiply 5 times 5.5, it gives us 27.5, and we subtract 27.5 from 60, it gives us 32.5. Now, as the air flows back down the mountain, it will heat up, because we know that as air sinks, or as air comes down, it heats up. But it will heat up at the same rate, at the dry adiabatic rate. And so in order to get the temperature on the other side of the mountain, we would simply multiply again 5 times 5.5, we get 27.5. But this time we add the 27.5 to 32.5. And we get, again, 60 degrees Fahrenheit. In other words, it's going to be 27.5 degrees warmer at the base of the mountain on the other side than it is at the top at 5,000 feet. But we still don't have any condensation. And the reason for this is that, if you remember, a temperature of 30 degrees Fahrenheit is needed in order for condensation to occur. But this heated air cools off to only a minimum of 32.5 degrees Fahrenheit at the top of the mountain, which is not enough cooling in order for this 1.9 grains of water vapor to be released. The air essentially would have to rise even further in order for the 30 degrees Fahrenheit to be reached. And so there's no condensation. Well, let's look at another example where we will have condensation as this rising air cools off. Let's look at a situation where there is more water vapor in the atmosphere. Now, if you remember in our discussion of moisture, we found out that one of the ways in which air is likely to condense the water vapor that's in it is to simply add more water vapor to the atmosphere. And when you add more water vapor to the atmosphere, the relative humidity goes up, and you have a greater likelihood of the air becoming saturated and eventually having condensation. And so in this example, this last example, we assume that we have 3 grains of water vapor in the atmosphere instead of 1.9 grains of water vapor. The air with 3 grains of water vapor in it will need a temperature of only 43.5 degrees Fahrenheit in order for the air to condense the water vapor that's in it. And this is a very important difference in this example from the previous example. There's more water vapor in the atmosphere, 3 grains of water vapor instead of 1.9. And because of the greater amount of water vapor in the atmosphere, the air does not have to cool off as much in order to condense. And the specific dew point temperature is 43.5 degrees Fahrenheit. And so what that tells us is that the air does not have to travel as far up the mountain in order for it to reach the temperature that's needed for condensation. And as is indicated by the illustration here, as the air moves up the mountain, the dew point temperature is reached at 3,000 feet. In other words, at 3,000 feet, temperature is 43.5 degrees Fahrenheit, which is the dew point, as we know. As the air continues to rise, it will continue to cool off. Now, it's very important to keep in mind that there is a drastic difference in the rate at which the temperature of the rising air decreases as it moves beyond the dew point temperature. As the rising air gets up to the dew point elevation, 3,000 feet, it will cool off at the dry adiabatic rate, which is 5.5 degrees Fahrenheit per 1,000 feet. At 3,000 feet, you're going to have condensation. You're going to have the water vapor condensing from a gas to a liquid. You're going to have clouds developing. And so you're going to have wet air. And from this point, at this elevation, the air is going to continue to rise because it's still warmer than the surrounding air. But it's going to rise and cool off at the wet adiabatic rate instead of the dry adiabatic rate. Now, the wet adiabatic rate is only 3.2 degrees Fahrenheit. Okay? So let's see how we actually get this information. And as you record this, you need to follow the arrows. In other words, you can record this first, then follow the arrows around this way. So we can find out the temperature of the rising air at 3,000 feet, which we already know to be 43.5 degrees Fahrenheit. But we can do something similar to what we've done already. We simply multiply 3 times 5.5, it gives us 16.5. And then we subtract 16.5 from 60, the temperature of the heated air at the surface, and we get 43.5. So we've done this already. But suppose we did not know the elevation of dew point. We only knew the dew point temperature, which is 43.5 degrees Fahrenheit. We would need to find out the elevation of the dew point so that we can determine how far the air has to rise up in order to get to an elevation by which it will begin to condense, so that we can know whether to use the dry adiabatic rate and when to use the wet adiabatic rate. And so in order to find out the elevation of the dew point, what we need to do is to get the difference between the dew point temperature, which we already know, 43.5 degrees Fahrenheit, and the temperature of the heated air at the surface, which is 60 degrees Fahrenheit. We do the subtraction, and that gives us 16.5 degrees Fahrenheit. We divide whatever we get, in this case 16.5 degrees Fahrenheit, by the dry adiabatic rate, which is 5.5 degrees. And we get 3. And we translate this into thousands of feet. And so our elevation of the dew point is 3,000 feet. And so we know that the air has to rise up to this elevation in order for the dew point to be reached. We know that the air, as it rises up to this elevation, will cool off at the dry adiabatic rate, which is 5.5 degrees Fahrenheit per 1,000 feet. But after this point, after this elevation, the air is going to cool off at the wet adiabatic rate, because it will have passed the elevation of the dew point. So the question now becomes, how far will the air rise beyond the elevation of the dew point? And so we know that the top of the mountain is at 5,000 feet. So essentially the air is going to rise another 2,000 feet and cool off at the wet adiabatic rate, which is 3.2 degrees Fahrenheit per 1,000 feet. And so in order for us to get the exact number of feet at which the air will continue to rise above the dew point elevation, we simply subtract 3,000 from 5,000, which gives us 2,000. We know that as the air rises to 2,000 feet beyond the elevation of the dew point, it's going to cool off at 3.2 degrees Fahrenheit, the wet adiabatic rate. And so we do the same thing as we did before. We multiply 2 times 3.2 now, the wet adiabatic rate. It gives us 6.4. And then we subtract 6.4 from 43.5, the temperature at 3,000 feet. In other words, the temperature at the top of the mountain is going to be 6.4 degrees cooler than the temperature at 3,000 feet, the elevation of the dew point. And so we continue and subtract 6.4 from 43.5, which gives us 37.1, which is the temperature at 5,000 feet. Okay, so again, you need to remember the fact that as air moves up the mountain, it's going to cool off at the dry adiabatic rate until it reaches the dew point elevation. Beyond that elevation, the air is going to cool off at the wet adiabatic rate. Okay, any questions thus far? Okay, the last thing to remember is the fact that once the air reaches the top of the mountain, it will have lost all the moisture that's in it. And by the time the air descends back down the other side, it will essentially be dry again. And so as the air descends back down the other side of the mountain, we know that it's going to heat up. And it's going to heat up at the dry adiabatic rate, which again is 5.5 degrees Fahrenheit per 1,000 feet. And so we get the temperature at the base of the mountain on the other side, multiply 5 times 5.5, it gives us 27.5. And then we add 27.5 onto 37.1, because at the base of the mountain on the other side, it's going to be 27.5 degrees warmer than the temperature at the top of the mountain. And this gives us 64.6. We round this off to 65. So the temperature at the base of the mountain on the other side is 65 degrees Fahrenheit. Now, one interesting sidelight to this whole process is what happens as the air rises up the mountain. It reaches the dew point elevation, and it begins to cool off at a much slower rate. The air will cool off at a rate of 5.5 degrees Fahrenheit, as I've said a number of times, until it reaches the dew point elevation. Beyond the dew point elevation, the air will cool off at a much lower rate beyond the elevation of the dew point, specifically 3.2 degrees Fahrenheit per 1,000 feet. What is the reason for this lower rate of temperature decrease in wet air as it continues to rise? And I'm asking this as a question. Does anyone have an idea why the rate is different? The wet adiabatic rate is different from the dry adiabatic rate. No idea on that? It has to do with a part of the hydrologic cycle that we talked about earlier. What is needed in order for water to be evaporated in the first place? Heat is needed in order for water to be evaporated. You have standing water on the surface after a big thunderstorm, and this happens quite frequently during the summertime. You have a thunderstorm in the early afternoon, and then the sun comes out after the thunderstorm, and very shortly the standing water on the surface is evaporated. Well, obviously the standing water does not disappear, it simply changes its form from a liquid on the ground to a gas in the atmosphere. It becomes water vapor, in other words. But the important thing to remember is that heat is needed for that transformation, as we all know, for evaporation to take place. Now, when the same air that has been heated begins to rise, and it rises up and cools off to a point where it reaches the dew point, then, of course, you're going to have condensation, and you're going to have this water vapor being released back into the atmosphere. And as this water vapor is released back into the atmosphere, the heat that was needed to evaporate the water from the surface in the first place is released back into the atmosphere with it. So as a result, the air is warmer than what it would ordinarily be. And as a result, as this air continues to rise, it will cool off at a much slower rate, at a rate of 3.2 degrees Fahrenheit per 1,000 feet. But you might ask, after a thunderstorm, usually the temperature is a little cooler. Would you think? Is it a little cooler or a little warmer after a thunderstorm? What do you notice? I haven't noticed. Is it a little cooler? Cooler. It feels a little cooler, actually, after a thunderstorm. But the air is not really cooler than what it was before the thunderstorm. The reason being is that much of the moisture that's in the atmosphere before a thunderstorm, for example, before condensation takes place, once you have condensation taking place, and after you have a thunderstorm, say for example, having developed, then this moisture, this water vapor is released out of the atmosphere. And one of the reasons why it seems so warm during summer afternoons, for example, is because of the great amount of water vapor that's in the atmosphere. We call it humidity. It's very humid, and it seems to be very, very warm. And actually, the temperature, the actual temperature, might not be that high, but it feels much warmer because of the humidity. Well, oftentimes when you have, say, a thunderstorm, you have all this moisture being released into the atmosphere, you have heat being released into the atmosphere, but you don't have as much humidity. You don't have as much moisture in the atmosphere. So it doesn't feel as warm, even though in fact the air temperature may be warmer than what you might think. So that's one explanation for that particular occurrence. Okay, one last thing. And that is a graphic representation of what we've talked about. You can explain the adiabatic rate of heating and cooling by looking at a graph like this. This graph shows temperature along the horizontal axis at the bottom, and it shows elevation along the vertical axis to the left. As you can see, temperature goes from 30 degrees to 65 degrees from left to right, and elevation goes from 0 feet to 6,000 feet to the left. And so what you can do is plot the temperature that we've been talking about as it relates to the heated air and the surrounding air on a diagram like this. I'm not suggesting that you duplicate this diagram, but you need to remember the general configuration of the diagram. And so what you do in order to get your adiabatic lapse rate curve, which is right here, and your normal lapse rate curve, which is right here, you plot the temperature of the heated air at the surface, which is 60 degrees, and the temperature of the surrounding air at the surface, which is 50 degrees. So you make two plots. And then in order to draw your line representing both the adiabatic lapse rate and the normal lapse rate, you have to get the temperature for the second plot of the heated air and the surrounding air. And say, for example, we could get that second plot at 2,000 feet. And so you do it the same manner for heated air and surrounding air. The heated air at 2,000 feet, you multiply 2 times 5.5, get 11, you subtract 11, 60. And this gives you this particular plot right here. After you get this plot, you draw a line straight through to two plots. And this is your adiabatic lapse rate line. You do the same thing with surrounding air. At 2,000 feet, you multiply 2 times 3.5, normal lapse rate. You get 7, you subtract 7 from 50, and you get your second plot. So you draw a line through these two plots. Now eventually the two lines are going to meet And where the two lines meet will be the elevation where the temperature of the rising air is the same as the temperature of surrounding air. And this happens to be at 5,000 feet, where the temperature is 32.5 degrees Fahrenheit. And so we know at that particular elevation, we will have atmospheric stability. So this is another way of looking at this general process of atmospheric heating and cooling. And so this concludes our series of lectures on the adiabatic rate of heating and cooling as a part of the global environment. Okay, I'll see you all then on Monday.